So, a 65 kilogram athlete in a long jump event leaps with a velocity of 7.5 meters per second at an angle of 30 degrees to the horizontal. For the following questions, treat the athlete as a point mass. So its center of gravity is really what we're concerned about. Ignore air resistance and use gravity as 9.8 meters per second. What is the athlete's velocity at the highest point? Okay, so like I said, the first thing you want to do is resolve your vector into its horizontal and vertical components. So, there is our initial velocity of 7.5. And we are at 30 degrees to the horizontal. Okay, so this is going to be our velocity horizontal and our velocity vertical. So from trigonometry we can work these out. All the formulas are on the previous page. Okay, let's do it from first principles. So if we want the vertical velocity here, we've got the opposite and hypotenuse. So sine of 30 is going to be equal to VV on 7.5. So therefore VV will be 7.5 sine 30. Likewise, cos 30 will give us VH over 7.5. So therefore VH is going to be 7.5 cos 30. Oops. All right, so if you're comfortable with your trigonometry, you can do it that way. If you're not, just remember the formulas from the previous page or put that onto your cheat sheet or something like that. So 7.5 sine 30. I get 3.75 for this one. Now that's velocity, so it's meters per second. And this one is going to be 7.5 times cos 30, about 6.5. Okay, so the first thing we've done is broken down our initial velocity vector into the horizontal and vertical components. You're going to see why this is so important in a second. We want the athlete's velocity at the highest point. What's the shape of the path the athlete's going to take? It's going to be parabolic. All right? So over the course of the whole jump, it's going to be like that. We want the velocity at the highest point. We want the velocity there. What can we say straight away about the velocity at this point? Zero. It's a turning point. I heard zero. What's zero? Okay, so the gradient is zero. Our vertical velocity is going to be zero. Okay, at the highest point, the athlete isn't moving up or down. They're just moving horizontally. Now, assuming air resistance is taken out of the factor, or out of the equation, what do we know about the horizontal velocity from here to here? It's constant. So if there is no vertical velocity, and we know our horizontal velocity, this is the velocity of the athlete. 6.5 meters per second horizontally. There is no vertical component at the highest point. Therefore, it's only the horizontal, which is constant. So 6.5 is going to be the velocity of the athlete at the highest point. Now, if we're talking about velocity, we need a direction. So it'd be 6.5 horizontally. Okay, making sense? Anything there not making sense? Okay, so the next one, part B. What is the maximum height gained by the athlete's center of mass during the jump? Now, if the athlete is moving at a, constant velocity horizontally, that means if you only consider their vertical velocity, they are going to move up to their peak, then they are going to move back down to where they land. Okay, they'll be moving horizontally during this time as well, but if you only consider the vertical velocity, that's what's going to happen. Okay, so to find the maximum height, what's our vertical velocity at that point? 0. So our vertical velocity at the maximum height is 0. So if we know that, we can use our Suvat equations to solve this. Okay, so what do we know in terms of our Suvat? The mass, hang on, in terms of Suvat, we don't actually need mass for this. Acceleration, what's acceleration? 9.8. Now, it's kind of important that we do this the right way. So let's get our signs right. Let's call it negative 9.8. Okay, because acceleration is acting downwards. What else do we know? Which one? What's our initial velocity? 6.5? 7.5. Okay, neither. We're looking at vertical velocity. What's our initial vertical velocity? 3.75. If you look at the previous slide, we broke our initial velocity vector down into its two components. So an initial velocity is going to be 3.75. Now I've put that as positive because the initial velocity is acting in the opposite direction to acceleration. Okay, our initial velocity is 3.75 up. What else do we know? Sorry? Final velocity, what's that? 0. And what do we need to find? We need S. So, anyone remember which Suvat equation we can use? Oh, we don't have T. Ah, there you go. I heard someone say V squared. Remember this one? Okay, so a V squared, that's easy, that's 0. U squared, that'll be 3.75 squared, plus 2 times negative 9.8 times S. Why negative? Because acceleration is in an opposite direction to velocity. So we're calling acceleration, we're calling down negative and up positive. And the reason this comes out nicely is because on the right we have a negative number, 2 times 19.8 times S, so we can just add that to both sides. And we get 19.6 S equals 3.75 squared. Okay, so I've just done 2 times 9.8 is 19.6, and just moved this whole bit over to the other side. And so if we work this out, S is going to be equal to 3.75 squared divided by 19.6. .72, I get. What's our units? Meters. It's height. So our athlete is going to reach a maximum height of 0.72 meters. So this is why it's important to break it down into our components of our velocity vector. If we're talking about maximum height, we don't care about the horizontal velocity. That makes no difference whatsoever. It's just how high they're jumping and gravity and everything acting in that up-down plane. Okay? That's why I can't stress this enough. Break it into components anytime you have a projectile problem where it's shot at an angle. Every time. Okay. Assuming a return to the original height, what is the total time the athlete is in the air? Okay. Now this requires an assumption, and it's a good assumption, and it's one that you should be aware of. Our athlete, as they jump into the air, and as they come back down, their acceleration is the same. It's always negative 9.8. Here they're starting with a certain velocity and going to 0. Here they're starting with 0. They're going to reach that same velocity coming back down. This path is going to be symmetrical. Okay? If you go up, then down, your path is symmetrical. So however long it takes to reach your peak, it's going to take exactly the same amount of time to reach the ground again. Exactly. Okay? So we can use that assumption. Work out the time it takes to reach the maximum height and just double it to get back down. All right, so let's find the time it takes to get to the maximum height. This is my favorite Suvat equation because it's the easiest. All right, so we're going to start. This is on the way up. So what is our final velocity? What's v? 0. What is u? 3.75. What's a? 9.8. So negative 9.8, because again it's in the opposite direction, times t. Now, rearrange our equation and we get 9.8t equals 3.75. This is nice and easy maths. So t is 3.75 divided by 9.8. 0.38. Okay, so we have the time that our athlete is in the air for, 0.38 seconds. Now, this is the time it takes to get from 0 to the maximum height. So to get back down again, how long is it going to take? 0.38. It's going to take the same amount of time. Okay? So it'll take 0.38 to get up, 0.38 to get back down. So total time is going to be 0.38 times 2. That'll be 0.76. That is going to be the total time the athlete spends in the air.